ideas of doing 3D structural research, finding out more than just the images, and what kind of methods we're using in terms of instrumentation and software. Oops. And a few current results, but I would also like to emphasize more than anything how we can go beyond very simple models, get something more complex, get the complexities of the models, and get a second order accuracy in terms of using something more accurate than Hubble flow as a constraint for the 3D structure. Why I'm saying that, you will see. And in this sense also what kind of research we need to do to get better 3D reconstructions of these objects. Well, what I do basically, and a few others, is kind of like this. The observations are like digging out a dinosaur or this kind of stuff, and you have what you have. These are your images and your spectra, and now interpret. What is this? What does this look like in real life? You know, this is not the real animal. This is what I do. I take the observations and put it in this shape. It gives us a better idea what this looks like, what this animal is. And this has to be done the right way. So the theorists do the real models, which are kind of reconstructing or getting a better idea of how these animals work, how they grow, how they go from baby to being an adult, and how they move, and what their skin is like, and all that. That's about the idea. So we're looking at this intermediate step. Okay? Now, for astronomy, we have a few key problems. What is this? It's a straight line with two blobs at the end. Is that true? All these three other objects, if you look from here, they just look the same. Right? So there are ambiguities. How do we find out the third dimension along the side? That's the problem. Now, software, there are a few software packages around that you can use to do this. There's one important one that is special for submillimeter observations. ARTIST, or combined with LIME, apparently LIME does the radiation transfer, and ARTIST is more like the interface. I'm not very familiar with the software, but that's what some people use for submillimeter observations. There's a whole group doing development on this, and do several parts of the software. And they have used it, or this is an example of usage of that package in our context. It has been used in others. Of course, this Holman from Leuven in Belgium has done radiation transfer for these 3D spiral structures that we have been seeing around the HB stars. But this software requires you, just for the setup, to program in C. To set up the structure by programming the structures in C, set up a bunch of parameters. And I really don't like that. It's not my way of doing things. Other people do it like that. And but try to program this kind of structure in C. So it's no way to do it. And if this Eskimo looks a bit funny to you, it's right. It's not the real object, it's a simulation. It's a model, a 3D reconstruction. Done in Shape. Shape's our software. Has a different way of doing things. It's interactive. You model the object by modifying meshes. As you see them here, interactively in 3D, you can apply either manual modifications, you can give them any shape you want basically, and add more together and give them physical parameters to get in the end your nebula as a rendering, or your PV diagram spectrum, or very complex structures as you see on the right. This is the software that we have been using for most of our work in planetary nebulae and similar expanding nebulae. And what I will be showing, most of the work has been done here, including the hydro simulation, also has a hydro module. This is an example, the same example, CV Leo, that has been done as CO transfer, radiation transfer, in shape, same stuff as you've seen before, done in ARTIST and 9. CO is currently the only molecular transfer that it can do. Here's a nice result by Xia recently, who has explored how complex structures that you look at in different ways can unify many objects that we see. So basically here they have used 3 lobes that are kind of configured close to each other and have looked at them in different ways. They're not identical in all of them, but very similar, and many of the structures can be reproduced. Obviously not all of them are exactly what we are seeing, but it makes clear that you can be fooled by the projection effects. Projection effects are very important, and that's what we want to resolve. There are other examples, very nicely reproduced, based mainly on the images. Here's another case where multipolar outflows that they have dealt with, and here are models that are looked from different directions of the same object. And this is a tool that has helped us a lot for similar tools. This is the Manchester Shell spectrograph in San Pedro Martir in Mexico that has produced the catalog that Alberto has been talking about yesterday, and has been a real workhorse for us to produce 3D reconstructions based on not only images but kinematics. But the kinematics is what produces helps you get rid of the ambiguities along line of sight. And here's an example. Here's the Eskimo Nebula model that I showed before as a motivation. This is a PV diagram of the model in the model through the middle of the object here. Now this is side view of the model. Compared this with the Cat's Eye Nebula, they look very, very similar. Now, if you look at the Saturn Nebula and its model here, right? This is our model of the Saturn Nebula, seen from our position, and you turn this around along the axis. This is now the axis view of the same object compared to the Eskimo Nebula. And this is the PV diagram that you can't get by observations. You can't get this PV diagram from the observations. This is from this view of the model. And now compare that to the observed or the model observation on the model PV diagram of the observed Eskimo. Very, very similar. So what we could do with this is basically unify these 3 objects. They are basically the same structure, even though on the sky they look completely different. Eta Carina, that was really an amazing project. We reconstructed the Homunculus Nebula based on X-Shooter H2 molecular observations obtained by a group at Goddard Space Flight Center. And this is the reconstruction, 2 different views. This is our point of view, and this is from the backside. Basically the same structures. And now the interesting part is this protrusion and this protrusion. It was very faint in the observations. Actually, the observers hadn't seen it. It showed only by additional processing within shape. Now we reconstructed the structure, and you have these ridges in here and some spots in here, these holes, And now, the amazing thing is that independently, Tomadura and his colleagues at Clementel in Holland, they did simulations, hydro simulations of the interaction of the binary in the center on an elliptical orbit. And they obtained these structures, different views of them. And basically, there's a cone through the interaction of the two winds. And if you superimpose them, the way they reconstructed the direction of the cone from other observations, combined with their simulations. You put these together with the 3D reconstruction of the homunculus nebula and blow up the cone, which is just a little dot in the middle, of course, and then compare the directions. The cone is spot on with these two little protrusions. Of course, we have no idea why, but there must be a connection between the outer structure of the homunculus nebula and the binary in the middle, and the wind structure that they produce through the interaction. Turns out that also this ridge here and here have similar angles and directions or orientations as the binary orbit. And since these two protrusions have about 20 degrees from the equator, we speculate that the orbit might be inclined by 20 degrees. That's pure speculation, of course. Now, much of the work for the reconstruction is based on the fact that you assume some velocity law along the line of sight that gives you a relation between position and velocity. Now, this is a problem if you have a non-spherical object. Like here, we have this shock structure that we have been hearing about. If you go from the inside out along a certain direction, you have a very complicated velocity structure, which is not the Hubble flow at all. So you can't really use that for reconstruction if you do it like that. But if you take a shell, a particular shell, and then measure the velocity along different directions and plot it versus the distance, it turns out to be quite linear. But not really. And there's another point. Even if the magnitude of the velocity is kind of linear, the direction may change. And that direction, a small change in the direction has a huge impact in velocity in the PV diagrams, which you interpret as 3D structure. So, what we really need is second order precision. Otherwise, we look at these kind of animals, which were the first reconstructions that were done by the archaeologists, paleontologists, right? So, are we happy with this reconstruction, or do we want something like this? That's the question. If you want a better reconstruction, we need to take into account complications in the velocity field. Now, we use position velocity mapping of the velocity field in this way. We say that the velocity along the line of sight is proportional to the distance with some factor of k, which we still have to determine from some symmetry or so. It's not good enough. Here is a bipolar nebula that we analyzed in a lot of detail with many slits over it. Here are PV diagrams paired with the observation and the model. See all this nicely reproduced. But here is a slit that goes along the middle of the object. The others were transverse. If you look at the PV diagram, you see that it's kind of has a different shape than the nice, almost spherical bulbs around that these lobes have. It's different. It's like a pear. It's not like a circle. And if you look at, to reproduce this structure, we had to introduce a nonlinear relation for the velocity with the distance for the magnitude, and also introduce a deviation from the radial direction. And that's key. This produces basically this flaring of the PV diagram at mid-latitude. That's visible all over the place. Now, here's an exception, maybe, but only maybe. I had big hopes to get new observations of proper motions over the years now with the Hubble Space Telescope. Here's one example that was done a few years ago. And they measured the proper motion as a function of distance. It's nicely linear. That's beautiful. And this is a crisscross mapping of these vectors, and shows that it's really nicely Hubble because it's all concentrated in the middle and no really interesting structure. Now, these are hydro simulations that were done by Usganga last year, and they also determined the proper motions in the simulation of that kind of NGC 6302. And they found that the proper motion, well, in the near region is basically flat, nothing there, and then goes up, but is quite scattered, and it's kind of linear boundary, but not really nice. And if you look at the vector directions, they are all over the place. There's no real systematics here. And it's because the process of measuring proper motions in very filamentary structures is very difficult. It's very messy, and hopefully that becomes better in the future. Now, I did a quick simulation for this talk, hydro simulation in 3D of a structure like that, just to show what we need to do in terms of investigating the velocity fields with hydrodynamics. Here, I tried to make this pear-shaped nebula, 2 lobes, but this is an ejection of a high-mass shell in radial direction. Just plain mass ejected radially at different speeds depending on direction. This generates this shape. Now, this is a PV diagram. The contours are PV diagrams. So the contour actually reproduces the original cut through or the projected image of the object very nicely, which means that this is a Hubble flow. It has been conserved as a Hubble flow as it expands. Now, not exactly. Here's some flaring. If you incline the object to the line of sight and then get a PV diagram, again, the contours here compared to the actual projection, then you see some flaring on one side and the other, which is a typical artificial, how do you call it, the point symmetry that is introduced along the line of sight, which is not real. That's a part of the effect of this deviation of the vector direction of the velocity. But it's not bad. It's not bad at all. You know, it's a Hubble flow that is conserved. Now this is the actual object that is the way it should look like in a perfect ballistic expansion. Now this is different. I tried to make a similar shape now using a varying density in the ambient medium, but with a low density fast wind, isotropic wind. Now the expansion speed depends on the density environment. That's the only basic difference. Now here is the density, a cut through the density in the middle, which shows only the high density shell that is expanding. Now it looks kind of like a ghost, right? I differentiate it as colors, an inner shell and an outer part of this region, and also in the velocity field here. What is red here is also red here, and green correspondingly. As you can see that the velocity field is actually quite different in terms of direction of the vectors and the velocities for these two regions, which are not very far apart. And the PV diagrams are here on the right. The outer part has a completely different PV diagram as the inner part, which is mainly due to the change in the direction of the vectors near the shot. And then you superimpose them to compare what you would get for reconstruction, in a 3D reconstruction, assuming a Hubble flow. The outer shell is bad in this region. Here it's kind of okay. It's very nice down here. The outer shell is pretty bad in here. The intermediate latitudes again here. The other parts are okay. So we need to study the velocity fields in more detail to get better 3D reconstruction. Or if we have constraints on the structure, it is a tool to study the velocity field. We can turn this around, of course. Here's another hydro simulation of that kind of structure, maybe, but using a wind into a very irregular environment, a shell that is very irregular, and so the shocks go in different directions with different velocities, and you get this kind of structure. This is the PV diagram, flaring completely here near the upper region where it's actually very pointed. This is not pointed at all, so 3D reconstruction using the Hubble flow would go wrong completely. And here's the same, well, we have seen these earlier. These are simulations of a bullet and a jet. Bruce has shown something like that from their group. And these are the PV diagrams, typical bow shot PV diagrams, flaring near the ejection. And these are observations. Actually, they don't look very different. Resolution isn't good enough, but to see it in detail, but it's basically the same structure. It's a bow shot pattern, not a Hubble flow at all, at the tip of the objects. Here are simulations of multipolar objects, which are constructed by blowing a fast wind, low density wind, into an irregular shell, which then is blown into these multipolar shells or structures. Here a comparison with real objects. And the interesting thing that I want to show here is that in this kind of objects you get kinematics. It's very interesting. Here is a projection of an object. Here's a slit, and this is the PV diagram, velocity. Oh no, this is a cut through along this slit direction. Okay, this is a cut of the spatial distribution. Look at this region. Now this is the PV diagram of exactly the same cut, which should correspond to the same structure. Here is a superposition of the cut with the PV diagram as a contour. Look at this region. Actually, the shocks go into each other, apparently. If you model this as in a 3D reconstruction, this would go completely wrong. Topology is wrong in this case. You would get the wrong topology. Actually, they are separated, but in the PV diagram, they go into each other. Here, Kinematic did a great job at reconstructing this object based on PV diagrams. These are the PV diagrams. Now, if you look at these PV diagrams, they are straight lines, vertical lines, like jets, basically, or cylinders that have transverse expansion. Here, there's a kind of indication of an inclination, which is kind of Hubble flow. But clearly, this is not a Hubble flow, right? Because these are vertical lines. Initially, they modeled them as Hubble flows, but I intervened and said, no, we need to add a cylindrical component, and then the reproduction was much better. And here's a simulation I tried to do using a disk and confining medium to get this structure. Actually, it's very hard not to confine an outflow like that. Almost any concentration of mass or density in the equator produces a very nice collimation of jets. And here's the PV diagram. It quite nicely reproduces the PV diagrams that have been observed. And this is the Southern Cross. PV diagrams in different directions up here, observed. And this is the model that Klein produced. And these are the PV diagrams, and this is the object. Now, shape has the possibility to really add particles you can draw on a surface, on these mesh surfaces, that allows you to reproduce each of these small-scale structures. Why would one do that? That's kind of like painting clouds. You would say it's nice and all, but is it any use? Well, it turns out that two of these clumps, this one and that one, fall out of place. They are out of place. So the reconstruction actually showed that these appear to be along the line of sight, along the axis of the object. They are not in the same regions on the hourglass as the other nodes. They are different. You know, there are these collimated areas up here and down here. So they might be a residual of something that was left on the axis. And to finish, I would like to show you this beautiful book that some folk all have seen, I guess. And well, he calls them butterflies. Butterflies should fly, shouldn't they? They fly. They are really nice. They have so beautiful wings, and actually, it would be really nice to see them fly. So I think, well, in the second edition, I hope he will change the cover picture in something like that. And hopefully it's electronic, so we can really make them fly. I apologize for the details of the flight pattern, but this was all done in shape. In case you don't want to do science, you just want to have fun, you can also do this in shape. Okay, as a summary, I leave it here. Thank you.
Okay, time for questions.
I know about one of the objects you talked about, Ada, of course, and I must say that it encourages skepticism about the whole deal. You quoted some models by Madura et al. Those models got a lot of attention in the semi-popular press. They consisted almost entirely of assumptions. The authors of those models did not know the relative strengths of the two winds. They did not know the opening angles of the shocks. They did not know the periastron longitude of the orbit, and they did not take into account the fact that the wind ratios and the opening angles were certainly different 50 years ago, and were certainly more different than that 100 years ago, which would have been the times when at least they could possibly have affected the shape of the homunculus. Essentially, my complaint is that what was portrayed as models, and when you read about those models, please remember this, they depend on far more assumptions and adjustable parameters than there are observables. The authors simply made assumptions in order to make their pictures look as good as possible.
Okay, my main point here is that may be true, but they have a paper, as far as I understand, where they use observations to constrain the direction and some of the parameters of the model. There are always assumptions, of course. But my main point is that the analysis of the observations with our model coincided in such a beautiful way with their results that both kind of reinforced each other. So you could use this now as a constraint to their model and vice versa. So nobody says that it must be perfectly all right, but it's a hint that something might be in it, right? That's all.
Okay, Sylvie.
Yeah, I'm just referring to a second step. There's actually some of now. Actually, 20 years ago, we spent a lot of time with Manchester shell spectrograph and AAT. And that time I was looking for the evidence of shocks in some of the second nebula. Then we used Manchester shell spectrum to try to map the 577 line and 4363 using many slits stacked over across the nebula. And I think I finished the 577 line. So we can actually produce a very nice PV-based diagram for you for the whole nebula. But I have to dig out the data and never get it published. Okay, so 799.
Yes. Okay, Quentin?
Nice talk, Wolfgang. You know I'm a fan of shape. One thing you didn't mention though, and I think it's something that is really good for this field, is the use of integral field units. So instead of having slips, you can actually get a sort of three X, Y, and Z simultaneously across a resolved object like a planetary nebula. So it's a really powerful way of integrating that 3D data cubes with morphokinematical modeling with shape.
Yeah, they are perfect, of course, in coverage, which we really need best coverage possible. One problem I see at the moment still is that they usually don't have the spectral resolution that we want, which is of the order of at least 10 kilometers per second, I think.
The Koala instrument on the AT gets close to that now.
Okay, great, fantastic.
Okay, Stefan.
Just two comments. You know for 20 years, or more than 20 years, that even the simple one-dimensional or spherical models do not show homologous expansion. As I said yesterday or emphasized, we have two distinct shells with two different velocity laws. I think that should be put into your model.
Oh, it's there. Oh, in the models.
In the model.
Yes,
The model.
that's my point. That's
Yeah,
what I want to show.
the faster
That
and
you need
smoother.
better velocity laws. Or turn it around, you need to deduce the velocity from the observation.
Yeah, but not very often you put this linear law. into your
Yeah,
model.
you shouldn't. We don't. We have to improve on that.
And
Okay,
the other is, I'm afraid if you make post-processing, the photoionization post-processing, that works only if you have very low density. Otherwise, the ionization will determine your hydrodynamics, and then post-processing is not working at all.
Yeah, we need that works only if you have fast shocks there. Shock dominated structure, that's true. Yes.
Okay, last question.
So my question concerns the assumption also. So we have 6 unknown x, y, z, dx, dy, dz. Okay. And so from we have 4 observables, y, z, dx, and integrated plus. Right? So you have the assumption on the velocity, and what is the other assumption? Because we are still
Yes.
missing one.
The k factor that maps the velocity to the position, you need to deduce it from some symmetry. When you have some kind of symmetry, even if it's only local, you can use that to find the relation between the velocity and the position. So you can stretch your PV diagram the right way. Right? That's important. You need additional constraints. And one important field of research for this is to find constraints. Improve the ways we can constrain the 3D reconstructions. It's something I would like to encourage people to do. Find better constraints.
Okay, thanks, Wolfgang. We move to the next speaker.